Hello everyone, I'm Jeeun, a PhD student at UT Austin, and I'm thrilled to introduce my research paper titled On the Performance of Jerk-Constrained Time-Optimal Trajectory Planning for Industrial Manipulators. This work stems from my summer internship at Dexterity, a company specializing in warehouse robotics platform development. In this field, maximizing productivity while completing the task without failure is very important. Therefore, I focused on solving time-optimal trajectory planning with third-order constraints, which can reduce jerky motions by smoothing the trajectories. And I have interesting results confirming that enforcing jerk limits in this way can enhance the performance of robots in practical applications. Let's begin by introducing the problem we are aiming to solve. In this paper, we focus on solving time-optimal trajectory planning, which is the problem of creating trajectories along a desired path that are as fast as possible, while satisfying the constraints such as velocity, torque, acceleration, and even jerk limits. Now let's move on to discussing the most typical way to solve the TOTP problem. First, given the path to track, we can parameterize the joint path Q as a function of a path parameter S. Then, our problem is now reduced to finding an optimal S of t from Q of t, which is much simpler because S is a scalar. Then, the joint velocity and acceleration, which we are interested in constraining, can be represented as functions of S dot and S double dot. And then considering the discretized system along the path parameter variable S and defining S dot square as the optimization variable X, we can rewrite the joint velocity and joint acceleration as a linear function of X. Therefore, we can reformulate first and second order constraints such as velocity, acceleration, and torque as linear inequalities of X. Finally, the TOTP problem is reduced to a simple linear programming problem with second or lower order constraints. However, by constraining up to second-order constraints alone, we cannot prevent sudden acceleration changes in the robot trajectory, which can lead to jerky motion. This highlights the necessity of incorporating jerk constraints. And here is a video that shows an example of what could happen due to jerky motion in the industry. So as you can see from the video, there are several reasons we need to include jerk constraints in the TOTP problem. First, we want a robot to track the given trajectory as precisely as possible. This is because undesirable spikes caused by poor trackability can result in energy inefficiency, and it can also damage the robot. Furthermore, we want to remove jerky motion to improve task success rates for tasks such as grasping objects, grinding, welding, dispensing, etc. To sum up, to ensure the robot follows the specified path as quickly, smoothly, and safely as possible, we impose up to third-order constraints during time-optimal trajectory planning. However, there are technical difficulties in including jerk limits in trajectory planning. As you can see from the formulation of jerk, unlike the second or lower-order constraints, which were linear forms of X, it has nonlinear terms remaining, meaning this cannot be directly formulated as a LP problem. In addition, since this is not an equality constraint, but an inequality constraint, approximated constraints may produce solutions violating the original constraints, which makes the problem very complicated. To address the issue, we linearize this nonlinear term using the fact that the function we want to linearize is convex on a series of x, which makes the real value always greater than the approximated value. Using this property, we can formulate the tighter jerk constraints to ensure that the solution obtained with the approximated constraints is always satisfying the original constraints as well. Now we can add approximated third-order constraints to the time-optimal trajectory planning, formulated as a sequential linear program where the linearization is required at every iteration until convergence. This enables the trajectory to maintain a significantly smoother velocity profile, as demonstrated by the plot figure on the right. Now let's move on to our interesting experiment results. To validate the performance of jerk-constrained time-optimal trajectories in real applications, we demonstrated typical motions commonly found in warehouse automation with and without jerk limits. We will first check how the TOTP results vary with and without the jerk limits. These are plots of velocity, acceleration, and jerk from the resulting trajectories for a front place motion. First, you see the proposed algorithm can constrain the jerk well, and this allows gradual change in acceleration, making the velocity profile much smoother, especially around the corner. However, as we added an additional jerk constraint to smooth the trajectory, the overall motion time was increased. Based on the sample motions we have tested, the motion duration, after adding jerk constraints, increased by around 3 to 5%. Additionally, due to the complexity of the problem, computation time also increased. When imposing jerk limits, we found that the computation time increases significantly by approximately 30 times. However, the problem can still be solved within 10 milliseconds using a C++ implementation, which is entirely acceptable for practical use. All right, it's time to share the most exciting part of this paper. To validate the tangible benefits of constraining jerk, we compared tracking performance on a real Kawasaki robot running the same path with and without jerk limits. Firstly, we compare the actual velocities of the robot. As you may observe, without jerk limits, when a robot experiences rapid changes in acceleration, it begins to deviate from its desired trajectory, resulting in overshooting and fluctuations. However, by imposing jerk limits, we can prevent those fluctuations very well. Consequently, the torque generated with jerk constraints tends to have less fluctuation, thus providing better efficiency in its usage. Finally, constraining jerk can also significantly reduce power usage. The experimental result shows that peak power can be decreased to 36% when jerk limits are applied. So these are our conclusions. First, we introduced a novel method to approximate general third-order constraints for TOTP, allowing iterative optimization to converge to the optimal solution. And then through real robot implementation results, we demonstrated the improvement in tracking performance and energy efficiency achieved by imposing jerk limits. However, we also found that the results can be sensitive to the discretization and splining of the path parameter variable, so in the future, we may want to explore optimal path parameterization, potentially co-optimized with the rest of the TOTP algorithm. That's pretty much all I had to present. Thanks for your attention.